We begin with the logic of hypothesis tests in general and of the chi-square test in particular, right? So the chi-square test in particular is used to assess if two variables that are measured at the categorical level are related in the population, right? Specifically, will allow us to assess if there is a relationship between two variables in the population by ruling out the possibility that the relationship we may observe in a contingency table from a sample is there due just to sampling error, right? So suppose that we're interested in finding out, let's say, if women and men have different levels of confidence in science and scientists in general, right? So the general social survey has a question for this, and they ask, which of the following options reflects your level of confidence in the scientific community? And they give some options like some confidence, a lot of confidence, or no confidence at all. And these are the results, right? So in the latest general social survey in 2018, here on the left, you see that 1,506 people responded to this question. 810 were female, 696 were men. And this is the answer choices they chose, right? A great deal, only some, and hardly any confidence, right? Now, the way we assess if there is a relationship, of course, is with relative frequencies. So we ask for percentages, and we see that there's some difference, right? While 50% of males, right, have a great deal of confidence in scientific community, 41% of female respondents have confidence in the scientific community, right? That's about a 10 percentage point difference. So it is quite quite a difference. So we see that there is a relationship here in this sample, right? That's what we would conclude. However, we need to rule out the possibility, if we want to make conclusions about the population or inferences about the population, we need to rule out the possibility that this difference is just there due to sampling error, right? And remember that sampling error is the difference between the population composition, right, and our sample composition, right? They are different. Because of the randomness, it's probably not going to look the same. The sample is not going to look exactly the same as the population. And that difference is just due to sampling error. So if we see a relationship between two variables in our sample, we need to rule out that relationship, or this difference in this case between male and female respondents, it's not there just by sampling error, right? That it is there in the population. So we want to test if two variables are related in the population, but remember that we can never observe the population, right? And we know that our sample doesn't look exactly like the population because of sampling error. So how can we do that, right? How can we make an inference from a sample, from a population that we don't know, about a population that we don't know and we will never be able to observe, and when we know that we have sampling error, right? That our sample does not look like the population. So that is why we do a hypothesis test, right? To make sure that the relationships that we observe on a sample are there as well in a population. Right? So now, how do we do that? What is the logic of a hypothesis test? Why does it work, or how does it work? Well, first, we accept the fact that we will never observe the population, right? We will never observe it. We just have the sample here. We don't know what the population looks like, really. But there's one thing we know. We know what a table or a relationship, a table would look like in the population where there was no relationship, right? In a population where there was no relationship, we would compare male and female, and they would have exactly the same percentages, right? If we had a population where there was no relationship, they would look exactly the same. That we know, right? We can make it up. We know that. So we begin with that we know. We don't know what our population is like. We don't know the relationship in our population, but we know what a population where there is no relationship would look like, right? Columns would be exactly the same. So we begin with a hypothesis that our sample table came from a population where there is no relationship, right? That's our null hypothesis. So there is no relationship in the population. Our sample came from that. We start with that hypothesis that there's no relationship in the population, because that's what we know. Well, I mean, we don't know if our sample came from there, but we know what a population where there's no relationship looks like. Now, it turns out that when we sample from a population where there's no relationship, right, these tables that we observe from there, if we calculate a test statistic for them, they follow a particular distribution. So samples that come from a population where there's no relationship, they follow a certain distribution, right? So if we know how the distribution of tables that come from a population where there's no relationship look like, right, then we can look at our table, right, and check if our table came from a population like that, right? How likely is that our table, that we don't know where it came from a population where there is, relationship or not, we can compare it to the tables that came from a population where there's no relationship, right? And we can see how likely it is that our table came from such a population where there's no relationship. When we compare them, if our table does not resemble tables from a population where the variables are not related, then we conclude that it is not likely that our table came from a population where the variables are not related. And if it's not likely that our table came from a population where there's no relationship, then we can reject that hypothesis and say, well, if it didn't come from a population where there's no relationship, it's very slim likelihood, then we can say that it came from a population where there is a relationship. That is the logic of a hypothesis test, right? That is why we start from a null hypothesis. If we have to explain this in graphical form, right? We don't know what the table in the population would look like, the one that we are trying to establish. We will never see that, right? We have a question mark there. We only see the sample, right? This is our table. Let's say it's a green. Let's say it's green for this. We see what it looks like. We see the percentages in there. We see this is our sample table. We won't know if it's coming from this population yet, right? We don't know. But what we know is what the population when there is no relationship would look like, right? In this population, this table, right? Red, big red here, would have column percentages that are exactly the same, right? Okay, so we hypothesize first that our table may have come from this population. There's no relationship in the population. That's the null hypothesis. Now, then we compare our table to the tables or the distribution of tables that come from a population where there is no relationship, right? And they would they follow the distribution, and they will look, you know, like they came from here. Now we compare our table to that one, right? And then if it doesn't look like our table came from this population, or doesn't seem to come from, you know, this, be distributed like these guys are, then we reject that it came from this red population, right? And we conclude, you know, because we rejected that is coming from such a population where there's no relationship, that is coming from a population where there is a relationship. That's how it works.